Yes, so Marco asked me to give an overview of the DR2, like the second wave of DESI results, specifically geared for particle physicists and giving a broad overview and context from galaxy surveys. So if you've read in details the papers, I'm sure you'll learn nothing new, but I hope I can provide some maybe practical context. So just to remind you why we started even doing that kind of surveys in the late 1920s to, independently Lemaitre proposed that a model where the universe was in expansion, and then Hubble observed this same, oops, yes, no, yes, okay, observed this same thing happening. Then the question was, well, how does the distance, since the universe is expanding, how does this distance measurement changes with epochs of the universe? I believe I had this conversation with folks here last week, which was, the Hubble parameter is measured to be about 70 kilometers per second per megaparsec, but until recently it could have been, or at least when I started studying physics, it was between 50 and 100. And I believe that I heard someone make the joke last week that the only reason we're now happily fighting over the area around 70 is because the proponents of the more extreme values have aged out of the field, and we're now allowed to focus our fight in this area. Yes, so the way that we started populating this relationship was looking at the very local universe using Cepheids, where if you can measure very precisely the Doppler shift, and if you had a relationship that gives you, and that's what spectroscopy provides, and if you have a very known relationship between the luminosity of an object and its distance, which, for example, Cepheid provides, then you're able to measure Hubble's law and this Hubble parameter. Now, if you project that to another type of objects that are slightly further away, that's what the two teams in the late 1990s and 1900s have done with supernovae. And they started then, they moved from here to then started populating this redshift versus basically how bright an object is. Ooh, sorry, I am struggling with this pointer. Right. Populating this diagram. And what they've shown is that as you move to higher redshift, even this relationship that they were trying to confirm, the supernovae appeared weaker than the relationship that they were testing, and therefore that showed that the universe was expanding and that this expansion was in acceleration. In other words, as brightness goes over 1r squared, then the distance increased further with redshift. And that was incompatible with a universe where you would have the assumption that the main components in this universe is matter. And so then that's where dark energy, the concept that is, there is something responsible for that accelerated expansion, but we don't know what it is. We have different explanations that we now want to test came up. And then the framework, therefore, in which we work is everything that particle physics has brought up, that if you look at the very recent and aged universe, you see a universe that is in accelerated expansion. And around the same time, you also had observations from the cosmic microwave backgrounds, and more specifically anisotropies in the temperature maps that would tell you that the universe was essentially much smaller and in causal distance very early on, which means that between here and there, massive expansion took place. And that framework, which is driven by what we've observed, is what we are working with and trying to test. And so another way to look at this framework that we're working within is really there's a complete relationship between what the components of the universe are and the geometry. We can see the geometry and access and measure the geometry, and so therefore we want to make inference about what is actually making up the universe. And when we show this pie diagram, we'll say, well, 5% is regular matter, and then 95% we don't know what it is, and that's really cool. But what I think is even more so interesting is we kind of assume that we have access to all the baryonic matter, which is, when you think about it, we have telescopes, which means that we're accessing photons, and we're collecting photons, but we're not collecting all of the photons that have ever been produced. We're just looking for a very short amount of time of the history of the universe and looking at whatever direction we have access to. So we're accessing less than 1% even of this total matter content, and we're still able to robustly, from those very short, very sampled observation, to have built the standard model robustly and now be nitpicking about details and more refined models, which I think is something to really appreciate, more than focusing on the fact that, yes, there's a lot that we don't know, but look at what we've been able to learn with what we have access to, which I think is pretty cool. But anyways, let's focus on what we don't know. We still want to learn what dark matter is, which represents, about 1/3, and dark energy, the other 2/3. So a lot of the DESI results that have been talked about have had to do with what the potential nature of dark energy has been. And another information in that pie that we need to learn a lot more on is about neutrinos, and in particular, what their mass is. And so I'll be able to touch on that DESI will be able to say something about that. Now, one more word about dark energy. Looking at the Einstein's field equation, really we see that this accelerated expansion touches, like I said, on the geometry, and that's what was proposed if it's entirely geometry with the cosmological constant. But then, is there an additional component which would have an equation of state, and then therefore how do you parameterize that? How do you express that? Or maybe even your assumption on geometry needs to be tweaked, and that's another line to which to go down in. That is, are there modifications that you might want to do on GR that could also reflect what you're observing? So these are at least what's set out to be tested by the measurements. And like I said, we collect photons. And what is it that we're actually trying to look at? And that's one feature, that is the Baryon acoustic oscillation. I think everyone here is pretty familiar, but let me just remind you. At recombination, photon in this primordial plasma, photons, electrons, protons are bumping into each other. Photons decouple, free stream. Protons and electrons form the first stars, and the first atoms, then eventually first stars for galaxies, and that happens preferentially where you have an overdensity of dark matter, except that this overdensity of dark matter is not completely random, right? And so if you have an overdensity here, that you had your plasma oscillating around it, photons decouple, you have a residual shell. And so you'll see preferentially structures, meaning stars, galaxies form here, but then also on that shell. stars and galaxies emit light. We collect photons. This is therefore what we're trying in an impressionist painting type of way to identify in this picture of the sky that we're taking. Now, the size of that shell is frozen once the photons decouple, and therefore the only thing that's going to affect the size of that shell is what the universe does itself, right? And therefore, if it expands, the size of that shell will expand. So at recombination, we have measured it to be around 150 kiloparsec, and now, however, 13.7 billion years later, it is 150 megaparsec. And so this is the size of the feature that we're wanting to measure. And if you look at a slice of this map that I was telling you about, you have basically a bunch of photons that then give you this impressionist painting that I was mentioning. And this is really the structures of the universe as seen in the first year of DESI. And this would be the relative size of the pattern that we're trying to measure. And so obviously, you know, it's an overlapping pattern, which gives this, these hues that you see here. And again, this would be the shell in the 2-point correlation function right here that's measured. And that's the measurement that gives us the basis for the discussions today. Something to mention as well is I've talked about galaxies. We also have earlier measurements coming from the intergalactic medium, gas clouds, and I'll touch on that a little bit later. But so really what DESI is measuring by making a very large 3D map and then slicing it into 2D maps at different distances is on one end, the angular diameter distance, which means by looking what's the apparent size of an object, that's one distance that's being measured. But then the other distance is this product of the radius at the drag epoch and the Hubble parameter that's degenerate, and that is along the line of sight. So these two distances encode the expansion history, and then we make all of our inferences from this. So this is where I would usually jump into telling you about DESI, the instrument, and all of that. But because I've been asked to be extra pedagogical for non-cosmologists, I figured actually I should go one step before. And before we actually measure galaxy spectra, it seems obvious, but we need to do a photometric survey. Which means we need to take pictures of the whole sky and figure out what it is actually that we want to be looking at. We've done this using 3 different telescopes, which are in both the northern and southern hemisphere. And we've surveyed about 18,000 square degree. And then for the nominal DESI survey, which was supposed to run for 5 years, we really focused on only 14,000. But we start with this. We start with an imaging map, which actually, you know, in practice actually looks like this is what we're starting with. And we say, okay, we want to be able to probe both across all the northern sky, because we're based in Arizona, what we want to look at, but then also in distance. So we need to pick out objects, because we're not like a photometric survey where you just get information about everything you point to. We need to make very definite choices as to which galaxies we're going to measure the redshift of. And so then we identify galaxies that will have the privilege to have a fiber put on them and then having their spectra measured. But how do we decide that we're actually going to look at these instead of like, you know, I can see there's one here, one here, one here. Well, one thing is we need to know that in the very limited amount of time that we have, which is very limited because we have a limited amount of money to run the telescope, which means that we need to have a certain number of galaxies within a certain time frame, which means we need to be absolutely certain that if we're putting a fiber somewhere, we're getting our money's worth. Then so we need to make choices. And then those choices, they also need to reflect at different distances, right, at different redshifts, that they're homogeneously probing the universe at that point, right? We cannot be, oh, this specific area of the volume that we're covering is easier for whatever reason, therefore we'll focus there. No, we need to make sure that over the entire volume of the survey that we'll look at, we have a representative sample of galaxies that we're picking. Yes. Oh, I mean, it's a zoom in. Mm-hmm. So it depends what your interests are, and so it can absolutely be, if this is your science case and this is the feature you're looking for, then you can make choices where actually volume for me doesn't play as much past a certain point, but I need X, Y, Z different. But then if you are working, and if you need to factor in different science cases, that's where the headache starts, because usually what happens is the other science case needs absolutely the opposite of what someone else needs, and then you need to optimize. And for example, it's, well, with only 1 year of data, who's gonna take the heat, and then when are we happy to have the best compromise for all the science cases, depending on the year and all of that. And so these are the considerations that happen when you make this selection. So do they need to have very strong feature? Means that, I mean, ideally you want them to have the strongest feature possible because it makes your job easier. But you only know that once you've taken the spectra, which means that from a bunch of images, you need to just take like you select them. So you cut out the little patch of the sky. Then you say from experience, which means previous imaging surveys and previous spectroscopic surveys, that kind of dot is that kind of a galaxy, which will give me that kind of a redshift success rate. And optimizing, and you only know once you've actually put a fiber on it, which means once you've wasted that time if it doesn't pan out. So then the preparation work to picking your targets is going to be a very big component of the success of the catalogs that you put out. Yes. So well, you get information about the color, the magnet in different bands and all of that. You've had previous surveys like SDSS, Sloan, and to inform on, and you make a plan, which is called the target selection. Sorry? Well, you're able to say if it lives in that color space and has that photometric redshift, then I am this confident that this is this type of galaxy, and therefore I know that with the instrument that we're building, the success rate should be this. But for example, quasars and stars look very much alike. And so not every object type is as easy, or at least you cannot be as confident. Your confidence depends also on the target type that you're looking at. No, I'm forgetting. It's different target class. Reds are the rarest, so I'm gonna go with, I think reds are the quasars, blue might be yeah, whatever, but it's different target classes. Yes, but so all of the circled ones are ones that we're going to observe. Yeah. So let me answer in two parts, which is the first one, I did not completely finish the target selection. I said we make a general plan, but then you build your instrument and you have what's called the survey validation, because you have a survey strategy, which is this target selection thing. And you will observe higher signal to noise and basically you go deeper in very select fields, which represented for us about 1% of the survey. And you validate your target selection, which means, oh, do you find that you indeed get this redshift success rate that you wanted for targets? Also, you do your science analysis on very small patches, so it's noisier and whatever, but you check, am I matching what I would be expecting for that volume, etc. And you can readjust. And you already have that before you start. So I don't know exactly which science case you're talking about, but so there are already a collection of deep fields that have been observed that are available. And then there is especially earlier in the survey, the changing anything or interrupting the normal running of operations was incredibly frowned upon. And as we've built on the footprint, we also have a secondary program, which is you can, as a DESI member, you can propose a survey that you want to do. So for example, redshift calibration for LSST was something that has been brought up, and therefore we've observed their deep drilling fields to build maybe a more complete catalog in that area. Or we want to look for Pathfinder, DESI to Spec S5. Well, can we look at different types of targets? What's the redshift success rate we get with the DESI instrument? What would need to be tweaked? And all those, if you wanted to do those future surveys, you can provide the data sample to get those answers. Now, for exterior people, find a DESI member to convince that your idea is great. And then we have external collaborators that in conjunction with DESI members can submit to the secondary program proposal. And it happens not regularly, but about every year and a half that there's a new review of new programs. And, maybe certain fields have gotten already, 5 hours of really like dedicated time on it. And then another type of programs that would interrupt the general flow of things is targets of opportunity. So for gravitational wave events, I think it's the only time that we actually would stop and point somewhere else. Supernovae, a bit less. Okay, yeah. Between 60 and 90%, but for targets that we've decided are worth the time, right? Because that's considered, let me rephrase. There's a whole set of, for example, galaxies that turn out to have, at least from where we're standing, no distinguishable feature. We could stay on them for 3 hours and still be not sure that we would get a redshift. And so, for example, when SphereX or again LSST was saying, oh, it would be great, like the spectroscopic sample that you're giving us is very biased because it's lacking XYZ population. Well, that's why. It's because we actually it is a very poor investment of time for a very, very unlikely success rate of getting a spectroscopic redshift. Mm-hmm. Mm-hmm. Yes. These ones? So they've been selected. So yes, we can put a fiber on each of those these individual fields. Now, if your question is, can we simultaneously put fibers and observe? I think let's say there are 8, all 8 of them at the same time. The answer is, this one and this one, yes. Those that are completely neighboring, no. But that we also have several passes at the same place of the sky. Well, basically, let's say we're observing this patch. We'll go about 2 to 3 times, have 2 to 3 passes, and we'll every time observe different objects, except for quasars that we're observing several times. But they're not for, I mean, it could be exceptional, like in exceptional cases, but otherwise, except for what is the Bright Galaxy Survey, where they're much closer, and that's kind of the point. They're also trying to measure that kind of thing. But there's so many choices that we can make that we will not purposefully go for 2 targets that are so close that we know that they're different, but that we could not resolve them. So, but it does happen that sometimes someone will post, oh, I see this spectra that is very, very weird. And someone, like a real astronomer, will be, oh yeah, no, you have a quasar at that redshift and a galaxy at that redshift. And it just so happens that it happens, but we can tell them apart. All right, so let's go to the spectroscopic part now. Now that you've done your survey of the sky and you've selected, those yellow dots, and you say, let's get the redshifts. Now you're actually entering into, you separate them into those different target classes that I mentioned. So you have the Bright Galaxy Survey, which is redshift up to redshift 0.4, that has about 30 million galaxies that is observed during bright time, meaning when the moon is out. And then all of the rest are the dark time or gray time targets, which means we don't want moon when we observe because they're further away and fainter. And that is the luminous red galaxies, the emission line galaxies, and the quasi-stellar object. And so they cover 0.4 to 1, and that is similar to what BOSS had. Then the real novelty here is this emission line galaxy sample that had been probed or at least tested as a cosmological probe with EBOS, and that overlaps with the emission line, with the luminous red galaxies, but also takes us to much further redshift. And finally, you have quasars that span basically this entire range, but they are at least an order of magnitude less dense on sky than any of the galaxies, which means that while they cover continuously a good redshift range, they are extremely noisy to measure with. Right. Okay, yes. Once I explain how we're using quasars to populate this, I'll show you, I'll answer that question. Just to say that, quasars act as backlight. You see as their spectra is getting redshifted, you see hydrogen absorption happening at 1216 angstrom. Basically those absorption feature allow you to know the redshift of the absorber, which is a hydrogen gas cloud. And so we use it to populate the higher end of that redshift of that 3D map. Moving on. Yes. So now the DESI instrument and why we have target classes that are not optimally overlapping if we were designing a survey with no constraints whatsoever and no real data. So you have the telescope that's here. What happens is you have a 4-meter mirror that then sends the light to this focal plane. This focal plane has the 5,000 low robotic positioner that have the optical fiber, and they bring it to the spectrographs, which is blue, red, and near infrared. And you have 10. So this is one spectrograph with 3 arms, and we have 10 of those that each will get 500 fibers and 500 objects. And so blue to near infrared means that on the blue end of the spectrographs, what we need the sensitivity for is for high redshift quasars. We want to be able to measure, one is the Lyman alpha emission line, and you have other emission lines there, but then this scribbles are the Lyman alpha forest, and they give you the higher end of that, Hubble diagram, so to speak. So you need a really good sensitivity in the blue in order to be able to have that information. Now, on the other end of the spectrum, looking at red and near infrared, this is the emission line galaxies. Emission line galaxies are more or less just a continuum, meaning no features, right? Except for this O2 doublet that if you have the sensitivity to resolve this O2 doublet, then you're able to get a reliable redshift for emission line galaxies. And that is actually your ability, like I said, other end of the spectrum, right? And the higher end. So your ability to resolve this O2 doublets basically sets the limits as to which emission line galaxy, with what's the redshift range, how you're crafting the population that you're going after. So these are the instrumental constraints to the building of the data, of the makeup of the catalogs that we're building with DESI. Yes. So the whole reason of doing a spectroscopic survey is that you want to do better than a photometric redshift. And so if you have, a doublet that you can resolve, you see this. And so you can quite literally, place this. But if you cannot resolve it, it means that what you're observing is this, and actually maybe even a little flatter. So then are you here? Are you here? That builds your uncertainty in redshift. And so if you build your uncertainty in redshift, you're losing the advantage of, and then the rest is flat, which means it's uninformative. Sorry, I say that again. Oh, as far as I understand, it's the only line, or at least the only feature that you see in that population of galaxy. We're not specifically looking for O2 because it's easier to resolve than something else. It's just that the only feature that we could identify by looking at this population of galaxy, the easier to pick out, let's say, is O2. In the same way that for quasars, they have other lines, like carbon 4, carbon 3, but the easiest feature, is the Lyman alpha emission peak, exactly. And so you go after low-hanging fruit. You go after the easiest thing that you can possibly do reliably, or as reliably as possible. Here? Oh, in the ELGs? Well, okay. Sorry, let me just... Actually, no, but I think, in black is your model, I actually think that if you look at in red the data, this is the model. You see nothing in the data here, and so that's which happens actually also. Sometimes you see the carbon-4 line. Sometimes it's just like a blob, and so all that to say that you need the most reliably showing feature that you can. Yes. Um, well, lower redshift means older. And so emission line galaxies, usually I mean, what we also see is they transition, they transition from being AGNs to emission, to going into like the galaxy regime. And so it has to do with the galaxy formation process. And, as they age, they become redder, and then they become your luminous, like the next population that you see. Yes, sure. I mean, I guess like the blanket answer I can give is that sure, we're interested in where they are to make inference on cosmological parameters, but actually those data sets, they hold a wealth of information for galaxy formation and galaxy physics and all of that. So, data sets available, go see them and use them for those purposes as well. Okay, so let me move on now to what, like an overview of the results. About a year and a half ago, we released well, actually, no, we released this year DR1, but that is the first year, the result of the first year of observations, but we actually presented the BAO results from the first year about a year and a half ago. And this already gives you 2 to 3 times more data in the same, let's say in the same footprint as SDSS. And now, after 3 years of observation, we improved, depending on the target class, compared to DR1, 2 to 3 times as well. So you see that between, after 1 year of observation, for we had completed about a third, right, 28%. After 3 years of observation, a fire that stopped our operations and a bunch of other external events, we still managed to get to 67%. And now early from the nominal footprint, and now we're hitting around the 5-year mark as far as data taking. And we've been close to 95% for like we've been doing really well in terms of collecting those data. Yes, so basically, if it's completely red, it's the final coverage. Final coverage means you've done all the different passes and you've hit all the targets. So for example, here, we started looking, but we still need more passes to pick out the targets that couldn't get gotten the first time around. So now we have redshifts and the positions of a bunch of galaxies, and we want to do the cosmological analysis. We blinded our data because we all have a lot of opinions about what results we might want to see from those cosmological analysis. So for galaxies, really, they blinded at the catalog level, which means they screwed with the redshifts and the weights, and went in and did their analysis, and that was fine. There's a subtlety with Lyman alpha forest because you are actually using not just the redshift, but you're using all the spectral information which means you need the actual redshift to understand your spectral information, whether it's contaminants from the instruments or whatnot. So the blinding happened not at the catalog level, but at the moment where we fit the BAO peak, we just add a shift of the BAO peak, and that's the way we blinded our analysis. Then we run the standard analysis that have been presented in year one. We have a set of mock data. We do data splits. We just run things. And then before we can unblind, we have a set of tests and that need to be successfully passed so that we can feel confident about the way that we've proceeded. So that's in theory, you unblind, you don't touch anything. So that's the idea. Now, something that is worth noting in terms of like the systematic budget is that between DR1 and DR2, because we had this result that usually what has been done is that you just fit lambda CDM and you measure cosmological parameters. Now we decided to also fit another model, and it gave interesting results that we're going to pursue more, which means that in the systematic budget for DR2, the fiducial cosmology related systematics were actually adjusted and increased. They went from about 0.1, basically doubled, to account for a fiducial cosmology that could have an evolving dark energy model. So that is one change that happened compared to the previous analysis that we gave, that we released. And what it resulted in is that it increased, sorry, the systematic error total of the distance measurements that we're measuring by 1 to 9%, basically it increased the error budget that we get in our BAO measurements, and this is still mitigated by then the precision that you get from having much higher sample. But if there's something to remember is that the results from the 3 year of data collected is still completely statistics limited. And this is in due part because of this modification that we did to account for now fitting a larger array of fiducial cosmology. The main systematic is survey volume and sampling density. Yes. Right. So then, this is a correlation function, 2D correlation of autocorrelation. This is a cross correlation. So you have the bright galaxy survey. So basically, all of these are different points on your Hubble diagram that is here. But the luminous red galaxies that go from 0.6 to 1.1, 1.2, are split into different bins. Now there is only one bin where you have the population, where you have two populations that are overlapping, and for the first time, DESI also combined those populations and fitted them and treated them together. And so this is how you go from 0.4 in redshift to 2.3 at the higher end of your basically Hubble diagram. And so here you have distance measurement by DESI over distance measurement by Planck. If they were in total agreement, this is this one line here. Here you can see that Planck, this is Planck for lambda CDM. And then what we overplotted as the dashed line is now if you fit this CPL, so omega naught omega A model with an evolving dark energy. So these are the modification that you would see. Now you have, what I've shown right now is each tracer is independent. You see in this 2D diagram, omega M and then the degenerate H naught RD, you see that each tracer has a degeneracy that is slightly different from one another, which means that the combined constraints are quite interesting and much tighter. And so that's one of the advantages to having this multi-tracer approach. And so if we're talking in terms of, figure of merit, the aggregated precision for measuring this BAO peak, now we've reached about 0.3% when previous surveys had percent level. So this is, one notable thing. Now, DESI, so in any case, so now those in this omega m H0 RD plan, you have omega m measurement about 3% and this 0.7 precision on this combined parameters. Right. So now a little bit more interesting in the sense less run of the mill is how do you combine and how does it compare with different probes? CMB for us in the latest release means Planck PR4 and the small scales coming from ACT DR6. So both of those are what we mean when we show CMB. And the dashed line here was the DESI DR1 results, and you see how we've shrunk. And it's very, the results between DR1 and DR2 are very consistent for DESI, and therefore, CMB then hasn't changed in 2 years significantly. And so the consistency, or at least the disagreement between both stays at around 2 sigma, which is by particle physics standard, obviously nothing to write home about. So for this, nothing has much changed. Now, if you look at what you get individually from large-scale structure, galaxy surveys, from CMB, and then from various sets of supernovae, you see that there's a good distribution, let's say, in omega m measurement, and that DESI is consistent with what DR1 had found. And so year 2 really does not, increases the precision, but doesn't change the results per se when we're looking here. And so another way to think about it, or at least that came after the DR1 results, is Tang et al. They really showed that the difference in the H0, or at least in the omega m discrepancies, and H0 and this, fitting or how agreement with time evolving models, they could be explained all simultaneously by either new physics or new systematics. And so the question now is, well, which one is it? And so I guess that's what's been exciting about having this input in the past few years. So I will now go through some of the figures that we printed out and talk about them a little bit. And I am happy, again, from discussions that we've had in the past couple of weeks. I've heard from maybe more particle physicists or theorists, well, we don't know what to do with what you're putting out because we don't know how to understand it. So feel free to point out what would be a more palatable and easy to interface with, at least from my own understanding. Yes. Mm. Yeah. Mm-hmm. Sorry, what's the question? Okay. Yes. No, wait. Well, okay. Let me skip to the end. So, no. Up. Something like, okay, so I see I'm running a little bit out of time. But so let me try and up. It's okay. Right. No, that is not this. So wait, play from current slides. This? Okay. Right. So now you have the equation of state of dark energy. Either this is one parameter or you have it evolving with time by introducing this WA, W naught. If you want to fit a cosmological constant, okay, W is 0, W naught -1. And so these are your references in terms of what you will compare, let's say, DESI results against. So now, if you take DESI alone, because that's one question I had earlier this week is, well, does DESI alone find that there's really reason to look at time-evolving dark energy model, or is it only once you combine it with other probes? So here, I'll point there and show that this dashed, this is the cosmological constant. Dashed again is the DESI DR1 result, and then DESI DR2 is in blue. So obviously here we're feeding a W naught model, but you can see that it's consistently between the two releases shows a reason to consider this parametrization just on its own. And so it's still within 2 sigma, so it finds agreement of lambda CDM, but the point is it really finds agreement with both, and so that's so to the first thing as whether this is taking DESI alone, you would also be tempted to look at those class of models. Now, when you combine with CMB, again fitting the CPL parameter, W naught, then you see that adding PR4 and ACT and DESI gives you now. It was still consistent with a cosmological constant. I mean, it was still overlapping with a cosmological constant, the 1 sigma contours with DR1. Now with DR2, you're increasing and you're seeing about 3 sigma preference for evolving dark energy. So yes, this gets stronger when you combine probes. Then again, putting the results that you had before and adding more is, what if you add supernovae? Then the question is, which supernovae sample? And say, let's look at all 3 main supernovae sample. And you see that they are also finding a way from a cosmological constant to various degrees. And so depending on which sample you want to consider, you're still in the 3 to 4 sigma preference for time-evolving dark energy when you add large-scale structure from DESI, CMB, and the anchoring at lower redshift. Again, now when we're discussing the robustness, CMB provides information from a very, very early time, and lensing will add, let's say, in terms of later information. So then you can wonder, well, does the result of adding CMB really changes if you consider lensing and the lensing? And you see that it, removing lensing weakens the preference, but you still see that same preference. So now, next robustness test is, okay, say you consider just DESI and the most extreme in terms of pulling you away from lambda CDM supernovae case, and then in green DESI and the CMB and the supernovae, do are you still getting pulled in the same region? And the answer is, in a sense, yes, to various degrees, but yes. Now, here it is that if you feed lambda CDM with geometrical probe, so CMB and BAO from large scale structure, it's the two colored curves that you see here. They are not in, obviously, I mean, they are in agreement with each other. However, once you feed lambda CDM to just supernovae, you see that it also agrees, right? But, sorry, yeah, here. But the point is that their constraints are, you know, discrepant in this mode and discrepant in this mode, and so the tensions you cannot have it three ways, is one way to say it, and so there's no good fit that takes all three measurements that come from these three different epochs together for lambda CDM, and so that's where now you consider something that is time evolving, and that's where you see that actually something time evolving now allows you to fit all of those three inputs. Whoops. So then, yes, so maybe the interesting point here is that there's a turn, there's an inflection point at 0.45 that shows that that in this scenario of an evolving dark energy, you have reached a maximum dark energy density, which really, you know, it's here, but it shows that compared to lambda CDM in recent epoch, the effect of dark energy is weaker than we would have had if it was a cosmological constant. And then if you go back in time, it's almost indistinguishable from lambda CDM. So I guess another way to put it is really lower redshift measurements and looking at this entire area is where the strongest, there's a lot of information to discriminate and to look for information as to whether what kind of model we might want to be testing, and observationally, that's where most of the information is. Yeah. So then, you know, and this is, I guess, the role of this workshop is to see, okay, we have different classes of models. And we have, you know, evident, like at least data that will hopefully also in the future complete this picture and refine it. And so how do we bridge both? And just to hammer the point, in green is the model, in blue dots is our data. And sure, we find a way from the model, right? And this is, let's say, BGS, LRG, ELG, and quasars. So we find a way from the model, but the error bars, compatible, tension. And so that's really where future, we should be paying close attention if we want to be able to make stronger statements. And just because I would be remiss to not point it out, the dark energy results have gotten a lot of attention, but DESI also looks at constraints on neutrino mass, which if you look at those constraints in the framework of lambda CDM, they're really cool because they would be the tightest constraints to date on the upper bound of neutrino mass, which would, you know, clearly cut out, like draw a clear line in the neutrino hierarchy. However, because now we're considering with more attention different base cosmology, well, that relaxes the constraints on neutrino, but it's still something to keep in mind. And I will just say, yes, okay, something has to give between very early universe, logical structure, supernovae, the lambda CDM model, like the cosmological constant is not surviving our observations, or at least it's showing cracks. But something that I also want to point out is we had DESI, the collaboration, we had a plan to observe until 2026, cover 14,000 square degree and be done in 5 years. We've done that ahead of time, and we've also been extended by 3 years, which means that now we have already started expanding our footprint and our observations. And the plan is going to be to extend our footprint about 20% by 20%, the overwhelming majority of it towards the south, down to deck 20, which means that we're actually increasing by a factor 2 the footprint overlap between Simon's Observatory and Rubin, LSST. And so I don't know, next 4 to 5 years should be exciting in terms of data sets and combined studies. And I will also point out that I'm personally more involved in the Lyman Alpha Forest studies. Davide is very active in the galaxy clustering analysis for DESI. Jamin, as you've heard, looks at higher order statistics. So at the discussion this afternoon, this is also maybe a really good moment to have all of us together and grill us if you want.